Good morning, everyone. My name is Dr. James Mitchell, and welcome back to Science Explained Properly. If you were here for the first lecture, welcome back. If this is your first time joining us, don't worry. Each lecture is designed to stand on its own, though they do build on each other over time. Today, we're talking about structure. Specifically, why does the universe have any structure at all? When you look up at the night sky, you see a load of stars. But those stars aren't scattered randomly. They're organized into galaxies. And those galaxies aren't scattered randomly either. They're arranged into clusters, superclusters, and filaments. A vast cosmic web stretching across billions of light years. The question we need to ask is, why? Why isn't the universe just a smooth, featureless cloud of gas? Why does it have galaxies, stars, planets, regions of incredible density separated by vast stretches of emptiness? The answer, as it turns out, comes down to a very simple idea that plays out over billions of years. Tiny differences become enormous structures. By the end of this lecture, you'll understand how the universe went from being almost perfectly smooth to the magnificently structured cosmos we see today. And you'll see that the same principle we talked about in the last lecture, gravity amplifying small imbalances, is responsible for almost everything we observe. So let's begin. If you could somehow travel back to the very early universe, say 380,000 years after the Big Bang, and take a snapshot of what matter looked like, you'd see something surprisingly boring, almost perfectly uniform. Hydrogen and helium gas, spread out across space with a density that varied by only about 1 part in 100,000. Think about that for a moment. Imagine a perfectly smooth sheet of water. Now imagine that in some places the water is 0.001% deeper than in other places. That's how smooth the early universe was. From a human perspective, you'd call it featureless. But from a physics perspective, those tiny differences, those 1 part in 100,000 fluctuations, were everything, because gravity noticed them. Now, let me explain what I mean by that. Gravity doesn't care about smooth. Gravity cares about slightly denser. If one region of space has even a tiny bit more matter than the region next to it, gravity pulls harder there. Not much harder, but consistently harder. And over time, millions and millions of years, that tiny difference compounds. Think of it like a savings account with compound interest. Some of you might have one of these accounts yourselves. If you deposit $100 and earn 1% interest, after 1 year you have $101. Not impressive. But leave it for 50 years and you don't just have $150. You have significantly more because each year's interest builds on the previous year's total. Gravity works the same way. A region that's 0.001% denser pulls in more matter, which makes it denser still, which makes it pull harder, which attracts even more matter. It's a feedback loop, and given enough time, those microscopic differences become galaxies. Now, here's where things get interesting. The process I just described, gravity amplifying tiny differences, works, but it works slowly. Too slowly, in fact. If the only matter in the universe were the atoms we're familiar with, hydrogen, helium, the stuff that makes stars and planets, gravity wouldn't have had enough time to build galaxies by now. The universe is only 13.8 billion years old. That sounds like a long time, but for gravity working on such tiny initial differences, it's barely enough. And yet, galaxies formed surprisingly early. We see fully formed galaxies less than 1 billion years after the Big Bang. So, something must have helped. That something is dark matter. Now, let me be clear about what dark matter is, and, importantly, what it isn't. Dark matter is not exotic or mystical. It's just matter that doesn't interact with light. It doesn't emit light. It doesn't absorb light. It doesn't reflect light, which means we can't see it directly, but it has mass. And mass means gravity. So we can detect dark matter by watching how it pulls on things we can see. We can think of it like wind. You can't see wind, but you can see what wind does. You see leaves moving. You see trees bending. You see waves forming on water. You know the wind is there because of its effects, not because you can see it directly. Dark matter is the same. We can't see it, but we can see what it does. We watch galaxies rotating faster than they should. We watch light bending around invisible mass. We watch clusters of galaxies held together by more gravity than visible matter can provide. The effects are unmistakable. Something with mass is there. We just can't see it with our eyes or our telescopes. That's dark matter. Not dark because it's sinister. Dark because it's invisible. Here's the crucial part. Dark matter makes up about 85% of all the matter in the universe. The atoms that make up stars, planets, and people, that's only 15%. Dark matter is the majority. Let me give you a construction analogy to make this a bit easier to understand. Imagine you're building a skyscraper. Before you add the windows, the walls, the floors, before any of it looks like a building, you put up a steel frame, a skeleton made of girders and beams. That frame is what holds everything up. It's what gives the building its shape. But once the building is finished, you can't see the frame anymore. It's hidden behind walls and glass. If you didn't know better, you might think the walls themselves were holding up the building, but they're not. The invisible frame is doing all the work. Dark matter is the frame. The galaxies, the stars, the gas clouds, all the matter we can see, that's the walls and windows. Beautiful, visible, impressive. But held up by something we can't see. An invisible structure doing the real work. And here's why that matters for structure. Dark matter doesn't interact with light, which means it doesn't get slowed down by radiation pressure. In the early universe, when everything was hot and dense, normal matter, hydrogen and helium, was constantly being pushed around by light. Photons colliding with atoms, creating pressure, preventing them from clumping together too quickly. But dark matter? It ignored all of that. It just responded to gravity. So while normal matter was being jostled and slowed, dark matter was already beginning to collapse. It started forming clumps. Those clumps created gravitational wells, deep dips in space-time where matter naturally fell inward. Dark matter built the scaffolding, and when the universe finally cooled enough for normal matter to stop being pushed around by light, it fell into the gravitational wells that dark matter had already created. Normal matter, the atoms that make stars and galaxies, filled in the framework that dark matter provided. We see the house, but the frame is what made it possible. So now we have dark matter creating gravitational wells, and we have normal matter falling into those wells. What happens next? The same feedback loop we talked about earlier, but now accelerated. Let me walk you through it step by step. We can call step 1 the initial clumping. In regions where dark matter has created a slight gravitational pull, normal matter begins to drift inward. Not quickly, not dramatically, just slowly over millions of years. But as matter accumulates, the gravitational pull gets stronger. And in step 2, the rich get richer. Here's the key idea. The denser a region becomes, the more strongly it pulls on surrounding matter, which makes it denser still, which increases the pull even more. It's like a snowball rolling down a hill. At first it's small and slow, but as it picks up more snow, it gets heavier. And as it gets heavier, it rolls faster. And as it rolls faster, it collects even more snow. Eventually, you don't have a snowball. You have an avalanche. In the universe, those avalanches become galaxies. Now, here's something interesting in step 3. As matter flows into the dense regions, it flows out of the less dense regions. Think of it like cities and countryside. When people move to cities, they leave the countryside behind. The cities get denser. The countryside gets emptier. The same thing happens in the universe. As matter collapses into the regions that are becoming galaxies, the regions in between become emptier and emptier. These are called voids, vast stretches of space with almost nothing in them. Not completely empty. There's still some gas, some dark matter. But compared to galaxies, they're deserts. And here's the strange part. Voids make up most of the universe's volume. If you could somehow measure all of space, most of it is empty. The matter, the galaxies, the stars, the planets, is all concentrated into a surprisingly small fraction of the total volume. It's like looking at a sponge. Most of the sponge is air. The structure, the solid part, is just the thin walls between the holes. The universe is the same. Galaxies are the walls. Voids are the holes. So now we have dense regions where galaxies are forming, and we have voids where almost nothing exists. But the structure doesn't stop there, because galaxies themselves aren't scattered randomly. They're organized. When astronomers map the locations of millions of galaxies, they see a pattern. Galaxies are arranged into filaments, long thread-like structures stretching across hundreds of millions of light years. Where filaments intersect, you get clusters, huge collections of galaxies bound together by gravity. And where multiple clusters come together, you get superclusters, the largest structures in the universe. This is the cosmic web, a vast, intricate network of matter with galaxies strung along like lights on a Christmas tree. And between the filaments, voids, enormous, nearly empty bubbles of space. Now, here's what I find remarkable about this. The cosmic web isn't designed. Nobody planned it. It's not the result of some cosmic blueprint. It's just gravity, doing what gravity does, amplifying tiny differences, pulling matter from low-density regions into high-density regions, building structure wherever it can. And given 13.8 billion years, those tiny differences, 1 part in 100,000, become a web spanning billions of light years. It's emergent complexity. Simple rules, followed over and over, producing something magnificent. Let's zoom in now. We've talked about the large-scale structure, the cosmic web, filaments, voids. But what about galaxies themselves? Why do they exist? Why doesn't matter just stay spread out or collapse into one enormous clump? The answer comes down to rotation. When a cloud of gas collapses under gravity, it doesn't fall straight inward, because nothing in the universe is perfectly still. Everything has at least a tiny bit of motion. Some sideways drift, some rotation. Think of it like this. Imagine spinning around with your arms stretched out. Now pull your arms in close to your body. What happens? You spin faster. This is called conservation of angular momentum. The same thing happens to collapsing gas clouds. As they shrink, they spin faster. And as they spin faster, the matter doesn't collapse into a single point. Instead, it flattens into a disk. Think of pizza dough. When you spin it, it spreads out into a flat circle. Collapsing gas clouds do the same thing. They form rotating disks of gas. And within those disks, stars begin to form. That's a galaxy, a rotating disk of gas and stars held together by gravity, sitting inside a halo of dark matter. But not all galaxies are disks. Some are elliptical, round or oval-shaped with no clear rotation. Why? because galaxies collide. When two disk galaxies merge, their stars get scrambled. The orderly rotation breaks down. What's left is a more chaotic, elliptical shape. So the shape of a galaxy tells you its history. Spiral galaxies like our Milky Way, those are relatively calm. They've had time to settle into a rotating disk. Elliptical galaxies, those are the survivors of collisions, messy, chaotic, reformed. Let's bring this back to us for a moment. Where do we fit in all of this? We live in the Milky Way galaxy, a spiral galaxy about 100,000 light-years across, containing roughly 200 billion stars. Our Sun is one of them, an ordinary star, orbiting the galactic center about 26,000 light-years out from the middle. The Milky Way, in turn, is part of a small group of galaxies called the Local Group. About 50 galaxies in total, most of them small. The two largest are the Milky Way and Andromeda. And the Local Group is part of the Virgo supercluster, a collection of thousands of galaxies spread across 110 million light-years. And the Virgo supercluster is part of an even larger structure called Laniakea, a supercluster of superclusters containing about 100,000 galaxies. We are deeply embedded in structure, our galaxy, our cluster, our supercluster. All of it connected by gravity, all of it shaped by the same process that started 13.8 billion years ago. Tiny differences, amplified over time. And here's something worth pausing on and taking some time to think through. When you look up at the night sky and see the Milky Way stretching across the darkness, you're seeing structure. Not just stars, but the result of billions of years of matter collapsing, rotating, organizing itself into something complex. You're seeing the cosmic web from the inside. You're part of it. Every atom in your body was forged in stars that formed within this structure. Every breath you take is made of oxygen created in the core of a star, scattered into space, and pulled into a new generation of stars and planets by the same gravitational forces that built galaxies. You are not separate from the structure of the universe. You are made of it. You are shaped by it. You exist because of it. Now, before we finish, I want to talk about limits. Because structure doesn't just keep growing forever. There's a point where gravity stops winning. In the very early universe, gravity and expansion were in competition. Gravity wanted to pull matter together. Expansion wanted to spread it apart. On small scales the size of galaxies or clusters, gravity won. Matter clumped together faster than expansion could pull it apart. But on very large scales larger than superclusters, expansion won. And here's the key point. The universe's expansion is accelerating. There's something called dark energy, a mysterious force that's pushing space apart faster and faster. We don't fully understand what dark energy is, but we know what it does. It makes expansion win, which means that beyond a certain scale, structure stops forming. The cosmic web we see today is, in some sense, frozen. New galaxies won't form in the voids. Existing superclusters won't merge into even larger structures, because expansion is pulling everything apart faster than gravity can bring it together. And here's the strange, slightly melancholy part. In the far future, trillions of years from now, galaxies outside our local group will have been carried so far away by expansion that their light will no longer reach us. The night sky will go dark. Future civilizations, if they exist, will look up and see only their own galaxy. They'll have no way of knowing that the universe is filled with billions of other galaxies. They'll think they live in an island of light surrounded by eternal darkness. They'll have no idea how much structure once existed. We live in a brief window of cosmic time when the universe is old enough to have built magnificent Structure, but young enough that we can still see most of it. We're lucky. All right. That brings us to the end of today's lecture. We started with a simple question. Why does the universe have structure? And what we've found is that structure emerges naturally from tiny imperfections. 1 part in 100,000. That's all it took. Gravity amplified those differences over billions of years, building the cosmic web, galaxies, clusters, filaments, and voids. Dark matter provided the scaffolding. Normal matter filled it in, and rotation gave us galaxies. None of it was designed. None of it required a plan. Just gravity, time, and the universe following its own rules. And here's the deeper point. Structure isn't random, but it also isn't predetermined. It emerges. From simplicity comes complexity. From smooth comes rough. From tiny differences come galaxies, stars, planets, and eventually, on at least one planet, life capable of looking out and wondering how it all came to be. You are part of that structure. The atoms in your body were pulled together by the same forces that built galaxies. The calcium in your bones, the iron in your blood, the oxygen you breathe. All of it forged in stars, scattered by supernovae, pulled into planets by gravity, and assembled into the most complex structures we know of. You, your brain, your thoughts. You are the universe's way of noticing its own structure. And again, that is not poetry. That is physics. In the next lecture, we'll shift our focus. But for now, take a moment. Think about what we've covered. The universe started smooth, and now it's filled with galaxies, stars, and minds. All because gravity never gives up. Thank you for listening. I'll see you in the next lecture.